So here we're going to use this very nice diagram from Dexter Perkins' online mineralogy textbook to look at amphibole compositions. This is, I guess we can call it the amphibole quad. And then down here we have the structure of amphiboles, nicely illustrated in the textbook by Klein and Dutrow, and also in that same textbook by Klein and Dutrow, a table that summarizes amphibole compositions. So let us start with an amphibole composition. So how could we write that? Well, we could write it in terms of the kinds of cations that we would put into the structure just in very general terms. We'll start with a W cation, and we can have either 0 or 1 atom of those. And then we can have fellows that we refer to as the X cations. We'll take 2 of those per formula unit. We'll take 5 fellows that are a Y cation, 8 of a Z, and then those cations will be charge balanced by 22 oxygens, and then 2 of either hydroxyl or fluorine. So we'll just write that like so. So the W cation, so this is the general formula for the composition. W and then X2Y5, Z8O22, and then OH and fluorine, some combination of 2 of those. So the W cations, these are the fellows that would go into the A sites. They would be in 10 or 12-fold coordination. So where are the A sites? We come over here, there are these big sites here. So let's first back up and take a look at the structure itself. Notice that we have a chain of tetrahedra here. So there's another tetrahedra there, 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 and there. And it's a double chain, so there's another chain here, here, and here. And they're linked by sharing oxygens there, and then out of the field of view here. So there's our double chain. And in between these double chains are these very large A sites. So those A sites can be left unfilled. If they are filled, then we would have that W cation be a 1 instead of 0. And the W cations that we would have, it looks like sodium is the major player there. We'll think a little bit of potassium could probably go into the A site as well under certain circumstances. So how about the X? The X cations are fellows that go into the M4 sites. The M4 sites are over here. So M stands for metal, and the metal cations that we put there are going to be in either 6-fold or 8-fold coordination. If we take a look at the M4 site in this table, we can see we could put magnesium or iron. Those would most likely go into the octahedral coordination, the 6-fold case, and then calcium would be in the cubic or distorted cube in the 8-fold case. So for the M4, depending on how these chains are twisted and turned and sharing oxygens with these other metal sites, it could be that they're bonded to 6 or 8 oxygens. So how about the Y sites? We're going to take 5 of these guys, and these are going to be the fellows in the M1 to M3 sites. So M1, M2, M3, those are here. You can see a wide variety of cations are going to go there, and all of these fellows are going to be in 6-fold coordination. Notice that that 6-fold coordinated site will also include things like titanium or 3+ iron or aluminum. And then in the Z, for the Z cations, these are the tetrahedral sites. There are 2 of them. There's a T1 and a T2. They have slightly different bonding geometries, but they are all in 4 coordination, hence we use T for tetrahedral. And then that is going to be almost completely containing silicon and aluminum, 4+. Over here we have the hydroxyl or fluorine. It's out of the field of view, but in the legend is indicating that that dashed circle would be the site of a hydroxyl or a fluorine. And you can see the M1s and M2s and M3s are all clustered over here. Those would be the Y cations. So now this table nicely lists out the possibilities in the name. Let's take a look at this quadrilateral diagram here. If we leave the W or the A site empty and have no W cations, then we would have all of the charge balance for the oxygen and hydroxyls being taken care of in the X and Y site. And so here you see it says M7. Well, this is a case for anthophyllite, where the X and Y are both filled by magnesium. And for grunerite, I've written over it a little bit, but you can still see there is an iron with a subscript 7. That would be the case where we fill all of the X and all of the Y with only iron. But there is solid solution between these two, so we get, instead of just pure grunerite, we can have the Cummingtonite grunerite series, where we mix in some magnesium, and then the amphipholite series, where we substitute a little bit of magnesium. But the bottom line is everything down here at the bottom end of this diagram contains nothing in the A site, so there are no W cations, and we have 7 atoms in the X and Y sites that are all magnesium and iron. Then we have a miscibility gap, and then we have tremolite to ferroactinolite, and then regular actinolite in between as a solid solution fellow. And this is the case where among these 7 cations, for the X cation, we will put in calcium. So notice that there is a 2 there. So the Ca with a subscript 2 means that that X cation is consisting entirely of calcium. True for tremolite, also true for actinolite. The real variation up here is what we're doing with the Y site. So we have Mg with a subscript 5 and Fe with a subscript 5, but we don't have to have just iron or just magnesium on the Y site. We can have extensive solid solution between magnesium and iron, and that's how we get our actinolite series. So this is where we get these names in thophyllite, cummingtonite, grunerite, ferroactinolite, etc. Where we get into these more complex fellows, hornblende, glaucophane, riebeckite, that's where we start mixing in other things besides just calcium and iron. So this is a very convenient way to illustrate the amphiboles, but it's also very, very simplistic compared to what we would find in a lot of igneous rocks where hornblende is very common. What's going on there is we're adding titanium into the Y site. We've got titanium here. Ferric iron, aluminum are also going into the Y site. If we're adding an additional charge, if we're putting in a 3+ cation like aluminum or iron or titanium into the Y site, we're going to charge balance that by putting in a lower charge cation, a sodium, let's say, into the M4 site. And then we can get things, the kinds of amphiboles that we would find in blue schists, glaucophane, riebeckite, or fedsonite, holmquistite, by doing the same kind of substitution, but by putting even more sodium into the M4 site, pulling out this calcium and filling up the M4, and maybe even putting some sodium into the A site. So these over here are very sodium-rich kinds of pyroxenes. So we have a wide variety of fellows. Let me correct one thing. I think I mistakenly said that titanium was 3+. Most of the titanium here is going to be in the 4+ state. It would actually be pretty rare to have titanium reduced to a 3+ state. So it's titanium 4 that would occasionally go into that Y+ site, and that excess charge would cause some sodium to go into the M4 site. In any case, very nice summary here in Klein and Dutrow to show the kinds of compositions that we can get. These are the quad components here that are illustrated in this diagram by Dexter Perkins, and then these non-quad components are also very important. They're not going to be illustrated in here. They're non-quad because they don't plot within this quadrilateral, but they're very important for understanding igneous and metamorphic systems.